see how this goes. So we're actually going to talk about how DC is generated, how AC is generated, what the difference is, and get us to inductance and self-inductance and go from there. So basically what we do when we generate AC and DC current, fundamentally we have the same thing. We're going to have a magnetic field, and usually what we have is that I'll have a loop of wire, and most of the time, because we can do it this way, we show it as a square. Okay, we show it as a square, and I'm going to have some sort of rotation for my loop of wire in my magnetic field. And the angle at any given time is going to be equal to our angular velocity plus our phase angle. At any given time, we're going to have that situation. So you can, and this right here is the value of the angle at time is equal to t equals 0. So if we can choose it, we usually get rid of the phase angle and we don't mess with it, right? If we can choose when we start, we can get rid of it. And so this is our angular speed of the rotation. And so if I look at my flux, flux is going to be however many turns of this thing that we have, the area of the loop, the strength of the magnetic field, and cosine of our angle. Okay? And we can do a couple of different things. If I look at my change in my flux with respect to time, or because this is, this is engineering physics, we're going to go ahead and write it that way. Really no difference. It's just how small my changes are, so I can integrate over them. Really no difference. But if I do that, and I'm doing this with respect to time, remember what this is going to do. If I make this NAB cosine omega t, go ahead and not worry about my phase angle, I'm going to get that this becomes minus omega NAB sine omega t. And we've seen that before, because remember, this is why I start out with simple harmonic motion, to be able to show the acceleration and the angular velocity if we start having something that works like that. Well, that right there is my EMF. And for whatever reason, okay, this is one of those weird facts of life, and physicists are weird, okay? We're just wired differently, we're just a little on the strange side. All of a sudden, we're going to write it as EMF instead of voltage. It's the same thing, okay? But we call this, because of tradition, we call this the EMF, or my electromotive force. It's still V is equal to IR. Guess what? E is equal to IR. We just like to confuse the issue. Okay? We like to confuse the issue. Now, when you get into circuit engineering, the circuit engineers are going to confuse the issue even more. So, and usually what's happened is they've been playing in the EMF world, because if you think about what we're really trying to do, we're engineers, right? Or we're trying to be engineers. And we want this thing to do something for us, right? We want it to do something for us. And so if we think about our water analogy, we want this to become a current pump for us. Hence, we're going to call it an electromotive force. Same difference, same calculations, same everything, except we're going to use the script E just to make life entertaining. But we get this right here. But this is the critical part. Look at that. We get a negative sign, and that's going to come to play in our inductance. That negative sign actually does work for us. The magnitude, of course, doesn't care whether it's positive or negative. Right? Magnitude doesn't care positive or negative. But that is going to care when I make my device. So let's make my device. So we're going to make my device. I'm going to come over here. We're going to make my device. So basically, if I'm going to do, we're going to make a generator here. Okay, we're going to make a generator. I'm going to have my handy dandy little loop that I'm going to allow to spin. And I'm going to go ahead and give myself a uniform magnetic field. And we usually see it drawn like this. This will be a north pole, and this will be a south pole. And we usually talk about this being a permanent magnet for the purposes of a generator. We usually do that. And it doesn't matter whether I have a DC generator or an AC generator, I'm going to have two things that are in common. One is that that magnetic field is constant and it's uniform, hence the permanent magnet. You want it to be constant and uniform, hence you're dealing with a permanent magnet. The other part is the charge or the change in the conductor induces the EMF, and I'm going to have a rotating coil. Now, I can rotate the magnets or I can rotate the coils. Generally, we rotate the coil. Right? I can do either or. But I generally rotate the coil because of the next part. Alright, the next part. So if I'm making an AC, this part of the wire, I will have a collar on the wire that's connected, and I'll have a second collar on the wire that's connected. Usually I have a little electric brush right here, okay? And I have a little brush right here, right? So what's happening in that system is that if I have this brush, and our book is great, by the way, and I have some sort of resistor or a light bulb, and this brush, what's happening as this rotates through the system, I can get current going this way, and then when it gets to the spot, current is equal to 0, and then all of a sudden I get current going that way. That's my AC generator. I'm going to alternate the current based on how this is turning through the field. And thinking about it, think about my right-hand rule. On one side, when it's oriented one way, it's going to go one direction. When it's oriented the other way, I'm flipping it, and my right-hand rule goes the other way. So I'm going to get the current depending on where things are. Now, if I've got a DC current, they call it a split brush. Okay, my DC current, I don't have a complete collar. I have a collar that has a gap in it. So what happens in AC current is I'm going to get something that looks like this. And in DC current, I'm going to get something that looks like this. Right? Right? Now, what happens is that in both cases, the magnitude of the current is not constant. Doesn't matter whether I have AC current or DC current, the magnitude of the current is not constant. Magnitude of the current is not constant. So, what I'm going to get is, I'm going to do it for AC and I'm going to do it for DC. AC, I get my little EMF, and it's going to be NBA omega sine omega t. So as I go through, and so I've lost my negative sign, sorta, because half the time it'll be negative, half the time it'll be positive based on how this rotates through, right? Because I'm going to be positive or negative as I go through. And my current will be NBA omega sine omega t divided by the resistance. Right? Remember, E is equal to IR we're switching E and I, you know, we get our, that backwards. No. Yeah, I did. You guys let me get away with it. Geniuses. E is equal to IR. Yeah. So I get E divided by R. I'm still not 100%. I'm still fighting whatever this crud is. So I get E over R, E over R. So you guys let me write it wrong and didn't say nothing. Shame on you. It's good old Ohm's law. Okay, so this is for AC current. For DC current, things don't look much different except for this. NBA omega, absolute value of omega t. I becomes NBA omega R, absolute value sine of omega t. I don't, you know, the forms of these two equations are the same, and I don't have anything different. Okay. So let's do a problem that shows you the issue between AC and DC circuits. I'm going to flip back to my problem here. Made it. There it is. Okay. So, basically what happens is, and if I actually am in a plant or someplace, I get a generator, right? And it's going to step up through a transformer, and we're going to get there in just a little bit. And we're going to go to our lovely power lines, and we're going to carry it across our power lines, ultimately back down to the house. Okay? So we're going to start with a DC generator. We're not going to worry about this part at all. We're going to say this transformer's not there. And we're going to take a DC generator, and it's going to supply 150 kilowatts of power. And the line is going to have a resistance of 0.25 ohms, which is a good thing. We don't want to have a very resistive line, A, because it's going to heat up, B, because I'm going to lose energy if I do that. I don't want to have that. And we're going to say that we have an EMF of 240 volts. I want to know what the current is in the system because we want to come up with a power loss. Okay, my power loss is going to be I squared R. So I need my current for my system. How much power am I going to lose for the transmission of this electricity? So power is going to equal IV. I've got V, I've got power, I'm going to figure out current. So current is going to be 150 times 10 to the third watts divided by 240 volts. It's going to give me 625 amps. Okay, so now I'm going to plug that in here. I got 625 squared times my resistance of 0.25. That ends up working out to be, we're going to lose 98 kilowatts of our 150 kilowatts just in transmission. This is the problem that Edison had. Edison wanted to do DC current, and if he does DC current, I've got to have short power lines, and I got to have DC generators essentially on every corner if I'm going to do this. Because I'm going to lose a heck of a lot of energy, a heck of a lot of power just in transmission. So what Tesla said, alright, so what Tesla said is, well, wait a second, we're going to see something else. If I can raise this voltage to a higher thing, alright, if I can raise this voltage to a higher thing, I might be able to save some stuff. So we're going to take a backwards piece. We're going to look at our AC again. And actually this works for DC too. Okay? Because we always have it changing. You know, the magnitude of the current is not constant. DC is going to look like this. AC looks like this. Okay? DC looks like that. AC looks like that. So, the maximum EMF that we're going to get is going to be when sine omega t is equal to 1. So that's going to be NVA omega. That's my maximum. And in the case of here, I'm going to go from Emax to minus Emax. I'm going to go back and forth. And now if I want to look at E average, and that's why I've actually posted this for the root mean square, even though we've seen the root mean square before, we're actually going to talk about what it means and why we get there, because it's really important in the electricity side. If I average over cycles, and I have complete cycles, my average is 0. That doesn't do me a whole lot of heck of good. That's not, you know, yeah, overall the average is 0, but I actually do have transmission, and I actually really am looking at it, and so we end up going back to look at the root mean square. And hence I gave you some information about the root mean square, because the root mean square is really calculating the average of a constantly changing value. Okay, the root mean square is calculating the average of the constantly changing value. So it gives us, it's a better way of looking at what's happening. So if I'm going to do that, we end up with the root mean square comes out of, I'm taking 1/2 of my NVA omega squared, and I end up with my NVA omega divided by the square root of 2. I get the same thing for current, right? I'm going to get the same thing for current. But this could also becomes my Emax divided by the square root of 2. Current root mean square is going to give me the same thing divided by the square root of 2. And I can look at power. Okay, I can look at power, and power average is actually going to be 1/2 Imax Emax. But I could substitute those values in there, and power becomes IRMS ERMS. Okay, so I actually can get this. So if I do this, and we go back and we use the power loss where I can step up that voltage. So I had a power loss if I did 240 volts. Now I'm going to do 24,000 RMS instead of my 24 volts. Power loss or we're going to do the other one. My current RMS is going to equal 5 times 10 to the 3 divided by my 24,000 volts gives me 6.25 amps. And then my power loss ends up being my 6.25 amps times my 0.25 ohms. I only lose 9.8 watts. So by being able to step up the voltage in the AC current, it's going to make that work and do long transmission lines lots easier, and I don't lose a whole lot of power over my system. So I can have Sooner Power Plant that's over there, you know, it's about, from here it's about 65 miles away, and it's still going to generate electricity to run Enid, or it's still going to generate electricity to run Tonkawa. And I don't have to have a generator on every corner. Problem is, voltage kills. And that's what Edison, you know, he wanted to say, that's dangerous. Well, it's one of the reasons why power lines are so high up, so that people don't necessarily run into that. That's one of the things that we work with. But that means we have to have something that steps it up or steps it down. And that's our transformer. Okay? And we saw from and so transformers, their basic way they work is this. We essentially have a Faraday inductance ring. Usually you see them as squares when we draw them as our pictures. I've got coils coming in here, and then I've got changes in coils coming over here, and my numbers of my coils are going to change depending on what I'm trying to do. So I end up having a primary and a secondary. And it's a matter of just which one is the primary and which one's the secondary that I work with. And you can go in and play with it, and you get that the voltage in the secondary, voltage in the primary is going to be related to the number of turns in the secondary and the number of turns in the primary. And if I do power in has to equal power out, i.e. mass balance. Except this isn't a mass balance, this is a charge balance, this is an electric balance. I have the current in the primary coil and the current times the voltage in the primary coil has got to equal the current in the secondary coil, the voltage in the secondary coil. And that gives me, if I do, I'm going to do VS, I'm going to get IP over IS. This gives me VS over VP. So I can actually write this as IP over IS. And any homework problems that you have just deals with those particular relationships. The big trick is building these things. And let me tell you what happens. When the snake comes in, it lays across these two things, creates a circuit, and it goes kaplooey. Not a good plan. They had plants that die sad deaths because the snake crawled up into the transformer. Squirrels will do it too. Not good plans. Not good plans. And usually what happens, and you've seen them, they're can transformers. You'll see them up here. They're can, you know, the ones that are on your telephone poles right outside houses. Yeah, those are can ones. And you'll get a variety of ones. Oh, it's November 1st. It's 1 o'clock, November 1st, so everybody's phone is going to buzz. You're all going to get a text message, you're all going to get an email, and our phones are all going to ring. Yeah, so that's what we get. And yeah, and things become ugly when the snake goes over and gets that part. All right. So that gets us into where we are. Now we talked about inductors. I think I did this part for you, showed you, at least wrote it out, because we were bouncing around and bouncing back and forth. You know, Q is equal to Q1 minus ET over tau. And this is for RC, and tau is equal to RC. Then we get current, and we get current, and we get 1 minus ET over tau. And this becomes, tau becomes L over R for inductors. And so we kind of talked about all of those. So where we're at now, so let's look at what we've got. This really gets us to chapter 33 of the text. So we've been kind of bouncing in and out of chapters 31, 30, 31, and 32. I've been kind of going in and out, in and out, in and out, getting the different pieces. But we're going to start now going from chapter 33, and we'll start playing with this a little bit better. So what we have, we've dealt with conductors, we've dealt with resistors, and we've dealt with what we call inductors. We know that inductors resist the change in current, right? Resist the change in current. These we take a little bit of time to fill up. So, in this one, the electric field is inside the capacitor. This one, we have a magnetic field. Inside the inductor. So we're going to start to see some parallels and start to see some things that are different. This one, we don't really have a field. We just got resistance. But this one's got an electric field, this one's got a magnetic field. This will store energy, this will store energy. Right? This one stores energy as energy, we'll do it this way. We'll just write it out. Energy is going to equal 1/2 CV squared. This one, energy equals 1/2 Li squared. So both of these things are going to store energy. One stores it associated with the electric field, one stores it associated with the magnetic field. We define capacitance as our permittivity of free space divided by D and the area of our capacitor. We talk about L being mu n squared, L for length area, or mu n squared, area divided by L. But these are the relationships for the number of turns. This is relationship to the area, and we can go back and forth. This one relates back to charge. Charge is CV. This one relates back to flux, and that's Li. And this goes back, if I look at my electric field, it's voltage divided by distance. This one is my magnetic field, and it's mu n I. So CATS has a really good table that kind of talks about what we've seen between the two different devices that we have. And our negative sign that we end up with the back EMF indicates that the voltage is always opposing the current. Okay? This is going to have voltage opposing the current when we go in there. So when we end up redoing Kirchhoff's rules and we're throwing in an inductor, we have to remember that our inductor is fighting the current. Tends to fight the current. The back EMF is fighting back against the change in current. Now once the current is steady, no big deal. Because there's no changing current, I'm not fighting a back EMF, I'm not creating a back EMF, and I'm not going to have a problem there. If I keep flipping through my notes here, we've gone back and forth. We've looked at power, we've looked at our AC generator. We've looked at self-inductance, we've looked at our RL circuits, and that's going to get us right up to chapter 33, and we're going to finish that up, and then we'll start talking about pointing vectors, Maxwell's equations, and do a little bit of history. Because that's what we have to do when we do electricity and magnetism. We have to do a little bit of history. And I think we're good. You guys over there doing good? I didn't lose anybody? Okay. Because I will tell you, one of the things that you have to get out of physics too, it's kind of universal, is AC and DC generators. Kirchhoff's rules, AC and DC generators, are the things that, when somebody says, well, did you get this? I got some things I got to make sure you got. For one odd reason, which I still haven't figured out, optics becomes a different issue. In the state of Oklahoma, we're arguing about optics. Most of us are on the side that you've got to have optics. OU's on the side of you don't have to have optics. OU's weird. Yeah, OU plays in its own little world. But then again, you got to remember those folks just created, if you haven't seen the announcement, OU just got a whole bunch of money and they broke ground on a quantum research center for quantum computing.